Well, I'm so glad that you all came here to talk about a subject that I'm interested in, but I got interested in it because other people were interested in it, and I got sort of taken in. So this is one of my volunteer kind of activities, working on energy sustainability, and lots of young people here. So you're the guys that are interested in energy sustainability, as I'm going to try to say. This is a very long-term issue that affects all society worldwide, and we have to figure out some way to deal with it. And it isn't my generation that's going to solve the problems, but it's your generation. So try to get some ideas of what maybe you can do. Whatever you're working on, this is an area where you can contribute. So that's kind of the gist of what I have to say before I even say anything, okay? And so personal perspectives, I'll tell you how I got into it as I go through my talk. So in the beginning, I give you some of the background, World Energy Outlook and Sustainability. So that's the reason I got roped into this. And this is a part-time activity that I do, but I think it's an activity that many people should do, and because everybody can contribute something different to it. So the next part is about nanostructures. That's sort of my thing. And so nanostructures is one kind of material system that can contribute to energy. There are many material systems that can contribute to energy, and there are many things that aren't material systems that can contribute to the subject matter that I'm talking about today. So this is really very broad, and it takes many talents. So here is the background part about it, that as you can see, the population of the world is increasing at a fast rate. Some years ago, so back here, so this is a couple of centuries ago, there were many people born, but they didn't survive very long, so population didn't increase. But then modern medicine came along, and the survival rate increased dramatically. And so this is sort of in my time. I was born in 1930, so somewhere in here, just when all this was starting. And it's continuing. And we're expecting maybe that the population will cap at about 10 billion people on the planet. And are we going to have resources for them? Well, you know, this is a question we can ask, and there are two sides to it. So, and I'll go into that in a moment. So here's the world's energy needs and the increases, and you could see that countries like the US and Canada, they're all the way up here on the top, a very large per capita energy consumption for one reason or another. And then there's the populations of the world that are very large down in this quadrant here: China, India, Brazil, and maybe a few others. And they're producing large numbers of people, but the quality of life has not reached the same level of energy consumption, but that's changing, and it's changing pretty rapidly. So if we translate these guys up in here, you could see that the requirements will be very high. So that gives you an idea. We don't really know how to extrapolate how much energy will be required. But when you go to talks on energy availability, you hear all these brilliant lectures by people with all kind of ideas, schemes, that we will meet those energy requirements. And I remember going to talks 50 years ago, a long time ago, and people were giving the same kind of talks that not enough energy. And we were down in this quadrant, well, where I showed you before, way down at much lower levels. So somehow we find the energy, and imagine that it is correct, that we will figure out, we're very creative human beings, and we'll figure out some way to increase the energy consumption. But are we going to be able to do the following? I'm going to go on into talking a little bit more about it. So the world's demands are increasing, but our ingenuity is also increasing, and probably will go away from the conventional oil, gas, and coal. But some combinations of this, shale oil, whatever, we're going to do different things than we're doing now, but production will increase. I believe that's true. The part that we're not as much tuned into is what it's going to do to our environment and the temperature of our planet. So CO2 is now at about 400, it's a little bit off the scale of this. So here it shows 380 parts per million according to volume. And that number is already over 400 now. Just measure it. And it's going up. Well, I guess a little bit more CO2 isn't so harmful. But the effect of CO2 changes the climate, so the temperature is increasing, and we've seen about 1 degree. We expect another 2 degrees in the next century. So is it hot here in the winter, in the summer? Not too bad. Okay. But some places on the planet might make a difference. But you could imagine that this cycle, 100 years beyond that, might be not so interesting. So CO2 is a problem, and can we figure out a way to have energy consumption without producing as much CO2 or using CO2 in some way? Well, the US, you don't hear very many talks about using CO2. In Europe, you hear lots of talks. There's quite a lot of research in the field, and they're having some success. It doesn't seem to be a topic of great interest in the US for some reason. I'm not sure why, but that might change with time. But anyhow, if we are to start today in trying to control CO2 levels directly, what we've already done to the atmosphere would take us many years to catch up on. So this is a very long-term project, and I'm not a person that has done calculations on this, and I would suggest that if there's an interest that you get such people, because there's a lot known about this subject. I'm not the right speaker, but it's something of interest. So we anticipate increasing uses of power because we have a standard of living, we have computers that we want to feed, and we have many other things that we like, so this will increase, and we have to figure out how to manage it. So we have many different sources. Fossil is the main one now. Nuclear has some potential, but some side effects that people worry about sometimes. Renewables is not very popular yet. That probably will increase dramatically in the next 100 years. Fusion is always a thing of the future. It hasn't yet made it into being production. It was 30 years away when I was young, and it's still maybe 30 years away now. So that's about where we are. So where do I come into this thing? You see here we have solar cells. Solar cells, that's photovoltaics. They take the red part of the spectrum. They operate in a certain wavelength region of the solar spectrum. Solar spectrum covers a much larger number of wavelengths. That's the blue part. And that comes in along with the solar in the form of heat. And that's what I'm going to talk about today, because there's a lot less activity, except at Santa Barbara. There's a whole bunch of people working on thermoelectrics. So I was very happy to come here and learn many things about what they were doing, because they're doing many exciting things. And they know more about this subject than I do, so invite them to come and talk. So a little bit about the background, nanostructures and why nanostructures and some of the challenges of materials. I'm going to be talking about those topics now. So, okay, why nanostructures? When I was growing up in research, we didn't have nanostructures very much, and so I learned about bulk materials. But then later on, I got into nanostructures, and nanostructures do have different materials properties because size is a parameter that you can use, just like temperature, pressure, and magnetic field, etc. And so why not try that and see what you can do? So I got involved with that about 20 years ago and have been working with that sort of generally and also in the energy field. So I'll be talking about some of my activities. But I'll also tell you that my activities in the energy field were inspired by people asking me to work in this. Usually in science, you work on something because it's your own idea to work in the field. But this is something that I was asked to work on. And maybe you'll get the idea that there's something you can do too, and so we can ask you. So catalysis is always an important thing in any kind of materials research, and it's very important in energy too to make materials that are different, that wouldn't be easily produced, but if you urge it along with the catalyst, you can make materials that would otherwise be difficult. So that's an interesting thing. And I like catalysis as a concept because catalysis is one part of science where you take a tiny thing and you get a big effect. So energy world needs tiny things that can make big effects. So if we think about the energy problem in terms of catalysis, I think that's a good model. I don't know how to do this exactly, but I believe that that would be a helpful way to look about it. When you think about some strategy, you should always be thinking about the impact that it may have at the outcomes, because we have a very big problem at hand, and what can we do with some small venture that would have an impact. Okay, now a little bit about what we've been doing in this decade. I had the privilege of being asked to head a National Academy study on challenges of materials research for this decade. And it's a good introduction to this kind of thing because we have kind of a large general audience. Many of you people don't work in this particular field, so you may want to know what we're trying to do. So there were 6 topics that were identified in this study. There was another parallel, a study that was conducted at exactly the same time, and the requirement was that the people on committee 1 wouldn't talk to the people on committee 2. And as far as I know, there was no communication between the 2 committees. And what was interesting about this is that the reports that were written by the 2 committees have a very, very large overlap. And so that was a test that was given to see if there was some universal answers to this, or this was just peculiar to the selection of participants on the committees. So maybe there's something in what I'm trying to tell you. That's the point I'm trying to make. So the 6 items in the study that I headed, the first one is how do complex phenomena emerge from simple ingredients? That means if you have individual electrons, you know sort of what they might behave like. But if you have an ensemble of electrons, it's very different because the electron-electron interaction is very important and it changes the behavior of an electron. Gas is different from an individual electron. That's what that is trying to say. Life is based on physical principles. We really don't know very much about it except that it's an out of equilibrium phenomena, but the physics of life is a really big subject, and we're not putting a whole lot of money and effort into trying to understand the difference between living and non-living systems and those kinds of things in a fundamental way. So maybe that's a good topic for somebody to work on. So what happens far from equilibrium and why? I'll have a couple of view graphs on that. I'll have a couple of view graphs on the fourth item about energy demands for the future. And the fifth one is information technology. That's received a lot of attention. I'm sure at this university, this is a major center for information technology, both from the software and hardware sides. And finally, the nano world. And that's going to be a big part of my talk. Okay, so out of equilibrium, you could see on your right there a swarm of fish. They're not uniformly distributed in the ocean, but they like to go in swarms. And why they like that, we don't really understand that, but that's a very common phenomenon. It happens in nature. It happens out in celestially, as shown. That's supposed to be a galaxy. And we don't have individual stars pepperminting the sky, but it's in clusters. There's an attractive gravitational force. That's important. And so out of equilibrium is important in material science. It allows us to make materials that are really exciting and interesting. I heard about many of them today. Many of the things you're talking about, you coax into being in some kind of stable state long enough so you can make it. So that's the good side of out of equilibrium, a good side. There's more than that. And then there's bad sides of it too, because you can have fracture and fatigue and all kinds of bad things happening. Disasters in the universe are usually out of equilibrium. So this is the information technology revolution. So when I was a young person, we started with big things. A computer was composed of elements that filled a room larger than this, and hardly had the power of, didn't have the power of your handheld cell phone. So we're getting smaller and smaller with time, and we're down to a single molecule. So what's next? And the devices based on a single molecule are really interesting. I think that's one of the forefront fields now. But what are we going to do after that? Well, I was here today listening to all the wonderful things that you're doing, so people are finding exciting things. They haven't hung up the baton yet. So in the nano world, some of the exciting areas are putting nanostructures together, and that's very popular here, and that's what this view graph is about. That's one of the forefront areas and being pursued very heavily by many people. And new materials in the bulk form is another new thing, and that's another thing that's very popular here, and you people are doing very well. Energy demands. As you could see, the world, that's a world map, supposed to be, and if you look here, it's not uniform. There's some very heavily lit up places here. That's the United States. And down here, California, Southern California, you can see you're well lit up. And then Europe is pretty well lit up, and Japan, and then you have dark continents. And that's going to change with time, and that's part of the demands. So in this report, and a number of reports, there are many hot fields that are identified. And so here's a list of some of the fields. Well, you people are big in solid state lighting, fuel cells. That's another thing you do very well here. Thermoelectric materials, I see here. Superconductors. And, well, PV, yeah, that's another thing you're big in. So there are many opportunities on this list that are heavily pursued here. So if people looking for research topics, you don't have far to go. Now I'm going to go to thermoelectrics, which is the topic of my, supposed to be my presentation. Why am I into this? I got into this, I tell you my personal, this is supposed to be my personal story. So I was invited by the government to work on thermoelectrics. They were interested in improving the operation of submarines. And they wanted to know, well, you know, water is cold and submarine has a fuel plant, right? They need energy to move, so there's a high temperature. So if you can make use of that temperature difference, you might be able to increase your fuel economy 10%, 5%, something. That would make a big difference. So that's what they were mostly interested in doing. And I had a visit from some high-level people from the government, came to MIT, sat down in my office, and asked me if I had any ideas what to do. So I said I didn't really have any ideas right off the spot, but I think about it. And that's what gave rise very soon thereafter to a paper that I wrote with a graduate student who walked into my office looking for a thesis topic. So, and we wrote 4 papers, and they're very well cited, but that work was done in about 1 month. And the student thought that research is pretty easy. You just go and you have an idea and you work on it for a couple of days and write a paper, come back. But then we didn't know if the ideas were any good and if they were correct. So he spent the next 3 years, but that wasn't so bad, 4 years for a PhD thesis and many citations. So not so bad. 3 years proving that the theory papers had some merit. Okay, so that's how I got into this, and I'll tell you what we were thinking. So the figure of merit tells how good a thermoelectric is. So that's this thing called ZT, and the nice thing about it is that ZT is approximately 1. And if you can do better, so 1 you can remember, that's a number, 1. And if you can do somewhat better than 1, you're doing well. And if you can do 2, that's our goal for this decade. So then you're doing really well. And it was hard to get to 1 at the time, 20 years ago when we started this field. But now many people can do 1.5 with some effort, at least in the laboratory. Maybe we can't do it for products yet, but it's coming along. Why is it good? Well, it's no moving parts in thermoelectrics. You just have a bar, and you have a temperature difference, like I said, between the submarine and the ocean. And so if you have a temperature gradient, you have different density of electrons across the bar. And that's what produces different density of electrons will produce a voltage. And the ratio between the temperature difference and the voltage is called the Seebeck coefficient. And some materials have a high Seebeck coefficient and other ones don't. So you look around for the materials that do. Well, it's not really so much looking if you want to do first order, because the material that we use today, and that's the best material, was the material that was discovered in 1954, and it's still the best material. That's bismuth telluride, and that's the commercial material today. But in the laboratory, we've done better than this, and so people are doing, and this university, there are a number of examples of doing better than this, and and there's hope for doing even better than we're doing today, because it used to be that there were no people working in this field, and now there are large numbers, so collaboration and exchange of ideas turns out to be important. So we're interested in all of these things, environmental friendly system. You can make hot spots, cold spots. You can do all kind of things like that. And you could recover waste heat and create energy from it. That sounds so wonderful. So the problem has been hard, and the reason is that it isn't easy to make this factor ZT, this figure of merit, greater than 1. Why? This Seebeck coefficient has the property it's a sort of intrinsic property of a material, but it depends on the carrier concentration. Here's carrier concentration, it's log plot. And you could see carriers increase, Seebeck coefficient goes down. Okay, that's the law of nature. But we want that to be large. At the same time, we want the electrical conductivity. The electrical conductivity is how well the electrons can move without being scattered. So you want it to get from one end to the other without being scattered. And to do that, you need carriers to carry electricity. And so we like a high carrier concentration. So here it's conductivity goes up. And you see, if you have high Seebeck, you don't have high conductivity. If you have high conductivity, you don't have high Seebeck. So you have a compromise, and this is your compromise. And so there's some carrier concentration that was very high for semiconductor, but we know how to make it now, and we've known for some time. So that's one of the challenges, how to do all of that, and at the same time to have a low thermal conductivity. But the thermal energy is carried by electrons also. And we have the electrons carrying electrical energy, and we have electrons carrying thermal energy. So they're proportional in some sense, at least the electronic part is proportional, and nothing we can do about that. So we have some compromises always in thermoelectrics, and that's why this problem has been difficult. So difficult. This is difficulty time. So here's a plot over time. So 1940 is sort of a beginning time, and just right after World War II, there was great activity in Russia, former Soviet Union, and much of the early work in this period was done there. But bismuth telluride actually was developed in the UK. So anyway, there was a big increase over a 10-year period from low, very low, to a figure of merit of 1. That's 1960. And then there was a 30-year period when not much happened. There were some papers published, but very little progress was made in the field that had any impact, long-lasting impact. And it was at this point that the government got antsy and wanted to have activity. So they started talking to me at 1990, that's sort of here on the scale, and I sort of started my first efforts in 1992, published efforts. You know, we were talking about we should do this, oh, who's going to do this, and, you know, like that. No background in the field, so what can we do? The first thing we did is figured out what's some strategy, and that's what I'm going to tell you. So the strategy that we came upon was to try to do small particles, do size as a variable that hadn't been tried before, thinking that the properties of small systems behave differently, that is, nano-sized systems behave differently from the bulk. So in 1990, there was some kind of advertisement to think nano. And so there were a lot of people thinking nano. I was thinking nano too, and I thought nano might be good for thermoelectrics. So that was my avocation. When I had nothing else to do, I might think about this a little bit. And you could see that what we do now is so we have these superlattices, and that's very popular here. And superlattices work very nicely in improving. That's work that you can hear from here. Or you could put little particles in, quantum dot superlattices, and that's also done here very well. And then you could take a bulk material and put nano inclusions into it. So that has been done by the group at Northwestern University very effectively. So there are different strategies that were introduced about 20 years ago. All of these things were started about that time. And they're responsible for this rise that has taken place here. These are just occasional occurrences. Most of that can't be reproduced very frequently, over this period. And it's only, I would say, in this decade that some reproducible results are really coming along. But in the last 10 years, it was just discovery kind of work. All right, so moving along, this is the summary of what I said. It's very hard to have high Seebeck coefficient and high electrical conductivity at the same time because the counter action of the components. And thermal conductivity and electrical conductivity like to go together, but thermoelectrics wants them to go opposite way. So it's hard to change that. So it's been a problem. And the government tells us we could have ZT of 3. We'd be very, very happy. But the goal for this century is ZT of 2. So that should be doable, right? And so people are working on it. So the idea that we had back in 1992 was to go to low dimensions. So I told you the story. The student came in looking for a thesis problem. I said, let's try a quantum well. That's different from infinite, so we go to 2 dimensions, and the density of states would be changed from 3 dimensions to 2 dimensions. And since almost all physical quantities depend on the density of electron states, so that should have something to do with something. And could we use that to make a better thermoelectric? So that makes a quantum well. The student came back, yeah, that really helps. So if a quantum well works, next week he was working on a quantum wire. That's 1 dimension. 2 dimensions is good, 1 dimension should be better. So we tried that one, and that was even better. And the quantum dot we didn't know how to make. They know how to make it here, but we didn't think we could make little tiny particles that were small enough to be interesting. But nowadays we can do that, so we have also quantum dots. And get, and I'll talk about it at the end of my talk today. So, so these were the ideas, and now we have done something. It wasn't only ideas, but the ideas have been implemented in the past 10, 15 years, and we have a whole bunch of different systems. This is all reported data. So this is a function of temperature. You see we have many thermoelectrics that operate with higher figures of merit. And we have materials that are both P-type and N-type. So let's take silicon germanium, for example. That's worked on here. So P-type and N-type. So the bulk and the nano are very different. The nano, you get big enhancement factors of 2 or 50%. So nano seems to be an effective strategy. And in fact, as you can see, people have been doing it for 20 years. And maybe I talk about that briefly, what ideas that we had. So the first few years were proof of principle. So when you do science in a new field that nobody knows anything about, you have to convince yourself that you have a direction of research that makes sense. So I call that the proof of principle stage. You're making just tiny quantities of something in the laboratory to prove to yourself that what you're thinking about isn't nonsense. The next step is to say, can we scale this up to make a material of gram size that's large enough that you can actually accomplish something with that material that's useful for society. So that was the next step. So what we did was, and this is where Gang Chen came in to the picture. He's a mechanical engineer, so he had good ideas about how to do scale up. So we have a lot of nanos here, little tiny nanoparticles, and we collect them. So we have many nanos. in order to, a single nano doesn't cool very much or doesn't generate much power because it's so tiny. You have only a few atoms that work. That's not going to accomplish anything for cooling a house or something like that. So you have to have many nanos. So that's what the idea is. So we put the nanos together. So here is nano in a bulk system. And here are nanos connected with other nanos. So nano A plus nano B. That's what the concept was. And our first experiments were to try to see if that concept, either of those, worked. And they both work. So you can do both. And there are many other, what people are doing here is they have ordered nanos too. That's even better. But this was our original idea and what we went and did. And so the simplest idea is you take a material that's a pretty good thermoelectric, maybe bismuth telluride or something. And so that's the picture over here on the left. And you grind it up to make it as nano as you know how. And that's the picture on the right. And you see if that does anything. So those were the first experiments that we tried to convince ourselves that mass scale that would also work. It wasn't enough to do it in the laboratory, but could we make something that was meaningful? So that was our effort at doing that. Now I'll show you some of the results. So the thermoelectric figure of merit is shown here. So the idea is we have to increase the Seebeck coefficient. So Seebeck is over here. And, well, we weren't totally successful. Here's the nano, the higher temperature here, about 150 C, it works. And here it doesn't work. But all the other factors worked well. So electrical conductivity, we could make nano with doping, propylene doping. You see nano improves for the same sample, just nano it and it improves. And thermal conductivity really gets much lower. So if you put the whole thing together, you get something that's very promising, 40%. So that was the very first effort that we had where we did, on the same samples, we did all of these things, show proof of principle works when you actually make larger quantities. So scale up was proved, and lots of other people have done much better than this, but this was, to my knowledge, probably an early work in the field. And the thing that was the most important was knocking down the thermal conductivity. The nano part of the lattice was the phonons that were the biggest effect. That's what we show with this. So this is for the totals, and this is now just the phonon contribution, and that was the most important individual part. So we understand a little bit about the science and where we're heading and somewhat why we're heading in that direction. Now, thermoelectricity is a very strange kind of field. When you read the literature, you're never quite sure that the people have done the experiment correctly. And the problem that is done is the theory is for all the parameters, electric current, thermal conductivity, Seebeck, everything you have to measure in the same way. You set up a coordinate system and you have to go with the same coordinates. And maybe half of the papers or a large fraction of the papers that you read in the literature don't make a careful effort at doing this, and they assume that these properties are isotropic, but they may or may not be isotropic. So you have to really read behind the lines and see that the people have done experiment correctly. Now there's always a test, and the test is, the proof of the pudding is that it really cools something by as much as you expect that it would if it had the properties that you said it had. So we know that, and we know how to calculate that. And so if you do something in thermoelectric, you should normally, at least with one sample, prove that the method that you're using produces the right temperature difference. So here we go. And this is as good as we were in this particular test for that system. Okay, now I'm going to go through some of the other things that, strategies. Up till now, I talked about proof of principle. So that was the first thing that we did. If you have a big center with lots of people working, then you could do all of these things simultaneously, perhaps. But this was all done with a very tiny research group of a couple people. So I never had a very big research group working on thermoelectrics. So we did things sequentially. Okay, so now we've shown that proof of principle, we've shown that you could scale it up. And now, what can we do that we can scale it up? We have a new technology. What can we do with it and improve it further? So the first idea was thermal conductivity is the most important thing. What can we do to decrease the thermal conductivity even more than we have up till now? So the first idea is introduce more scattering centers. Well, you can make the system more nano. You can put in little metal particles. I learned here visiting today that's a good way to do this. We didn't do this, but that could be done. So any kind of idea to reduce thermal conductivity is good. And so you have to do it with N and P type components because the device always has N and P type. So if it works for one kind of type and not the other, you haven't really solved your problem yet. So this shows that, yes, nano works for both N and P type. This is silicon germanium. You can use any other material. But this is something that's a good idea to do. And so the idea is, the physics behind all of this is you want to have within your grains, you have the grain boundaries, and then you have some defects like point scattering centers, something like that. So you put an impurity, either go substitutionally or interstitially, something like that. It will scatter, hopefully, phonons more than electrons. So you have to figure out how to do this. And people here have many ideas that go far beyond our ideas. But you can see that we have some kind of ordering in the material. You could see some local structures. And that's a good thing to have. So, okay. This is something I throw into the system now. We've been playing with this now since not over 20 years. And we have to start thinking of making materials available widely. So some materials in thermoelectrics, when you read the literature, are rather rare. They're not very abundant. And if everybody in the world decided to use these thermoelectrics, we wouldn't have enough for everybody. So it'd be nice to find thermoelectrics that are abundant. So the lead salts are good thermoelectric materials. Lead telluride and lead selenide have been studied very widely for thermoelectricity. Lead sulfide is not yet a very good thermoelectric. So we've been playing around and trying to make it better. But so this is just a principle that has to be developed, is to have a number of common materials. Silicon germanium is a good material. It's germanium part is not so common, but you only need about 5% germanium, and the rest can be silicon. Silicon is quite common, so that might work, but it's only good thermoelectric at very high temperatures. And for most applications, you want to be below 600 centigrade. So that's not the region for silicon germanium doesn't work there. So we need to find other ones. So this is just an advertisement of a principle that we're after, finding common, cheap, not so expensive anyway, available thermoelectrics that could be widely used. And so another thing is looking around for materials with interesting properties. So lead telluride is an interesting one. Normally we think of the small band gap that we have, there's an L point band gap, and here's the L point band gap. But there's another band that has, it's a heavy band, it has heavy mass carriers that if they could be included would be very good for making a P-type thermoelectric. So we have to have the right kind of dopant that would move this band up so the Fermi level would cross it. And that has been accomplished by a number of people. And this is one, Li Shi is here, and Jeff Snyder is, some people might recognize them. Here's some band gap engineering. That's another. So you play around with the band gaps, you move the bands around a little bit, doping, strain, something, figure out what to do. So this is an example of sodium-doped lead telluride, where engineering from the external side was used to bring that band that we want with the heavy holes up above the Fermi level successfully. So things like that. This is just ideas. You have to play around with the energy band. Every material has its own twerks, but there are opportunities, if you understand solid-state physics somewhat, to play around with these. So that's the first thing, is playing around with the bands to promote a higher ZT. Another thing that I learned, and this is playing around with the density of states. This has only been made to work, and it's even sometimes questionable whether it did work this way. But the concept is that if you could arrange a material that had a kind of a bump. So this is an extra density of states. The dashed line is what we teach you for just a simple material with no frills. But if you have some special kind of states like resonance states, that some particular impurity produces an additional density of states near the Fermi level, then you can benefit from that. So suppose you could do that, you could benefit from it. And this particular case, this paper claims from theory and experiment that they were able to benefit from it and get ZT going from sort of less than 1 to 1.5, so doubling. I'm not sure you believe this work, but the idea is a good one. And if you can come up with a system that really does this, the people don't doubt the idea, but they are not sure that the idea was really implemented in this work. So that you have to still prove. But the proof of the pudding is that the experiment worked in practice, but the reason for it is not completely understood. But let's say that they were able to do what they said, so that is a good approach. The third one that I have is modulation doping. So I was speaking with a large number of people here who participated in research at the former Bell Labs. And so I learned about this whole thing from Bell Labs papers. And so these people wrote a very important paper, modulation doping, that revolutionized semiconductor physics and devices based on semiconductors. This paper had a very large impact on devices, and so it was a Nobel Prize winning work. And so what the idea is you put carriers somewhere in some band, and you arrange things with a very small channel. So there's a very small tunneling barrier that you have to overcome so that you can transfer the carriers into a channel where they make a difference. And there they can affect the electronic states and the conduction pattern. So the idea is that, well, I can illustrate it here. For example, these places here will release carriers, and the carriers go into this channel here, which is a high conductivity channel. Here you have many dopants and scattering centers. So the electrons there get scattered and they don't transport very well through the material. But the electrons that are in here, they can go from one electrode to the other very easily. So we would like to have some kind of mechanism to inject carriers from here into this region and collect them. So that was the idea, and so we did this for thermoelectrics. So this is an idea from semiconductor physics. So what the take-home message from this is, if you have some knowledge about science, you can apply it to other fields. And that's exactly what we did in this case. And it really does work, and I'll show you. And this hasn't been perfected. This is just, and it's right now in the conceptual proof of principle form. So we take a material here. So this one is the intrinsic, and this one here is heavily doped. And we want to introduce some of this material into that. So here it is. And so, but we have a conduction path. So that's, we don't put too much in, so we still have a good conduction path. And this generates carriers that we want. And so we compare, to test whether we've done something, we compare a system that's like this with the same atoms, but we have the atoms uniformly spread out, okay? The same atoms, but one of them, we collect the atoms in these little red and yellow areas, and the other one, we have it spread out. And so this shows you that you're going to have an increase in sigma, in the electrical conductivity with modulation doping, because we have more carriers. So that makes sense. And the thermal conductivity is almost unchanged. So that's good. We're able to have the phonons seeing almost the same background, but the electrons behave differently, and that's what you want to do in a thermoelectric material. So this is just one idea that we have made. We made it work, sort of, and so the ZT went up by some few percent. This is just first effort, no optimization yet, but this kind of idea I think is pretty good, and I think it can be more widely applied and improved upon than we have in this initial work. We're not really doing much with it at the moment, so other people, it's available for many other people to try. So in my talk today, what I tried to do is first say a good knowledge of science is useful. We can use one field of science or things that we learned somewhere and apply it to other areas. Another take-home message is it's not a bad idea when called upon to give some fraction of your time trying to make the world a better place to live in, and you can use your science to do so often. Almost all the work that we did in the thermoelectricity field, at least for the first 10 years, we had no financial support. We just did it as sort of Saturday work, like for fun. And then we decided maybe we should get a little more serious after 10 years. So you can play around a little bit just to try out things very cheaply. And if it works, then you go into it more seriously. That's the take-home message that I give you if you care to take it. And nanosystems are interesting. They've been worked on now for about 20 years, but when you pick up the journals, you find something new every day. And I think that there's still many opportunities for young people in nanosystems. And any new ideas that you have are welcome. So we need new strategies for implementation once we show proof of principle. And what this particular field needs now is more new ideas, new concepts. I gave you a couple of ideas I had and that we're working on, but I'm sure that there are many others, and I heard that many others here. And they're not all from nanosystems, just in the bulk. I've heard many new things happening. And what's different about now and maybe 20 years ago or even 15 years ago is the large number of people interested in energy and energy security and starting energy centers, as you have started one here. And I think all of those things point to collaborative work, because many of these kind of projects, like I talked about today, require people that know how to make materials and people know how to measure them and people that have ideas about crazy things to try. And you need to put all these together to have success, I believe, in this energy game. So that's sort of my message, and I'd be happy to take questions.
I had a question about using, rather than have random alloys and scattering of phonons, given that the dimensions are now things you can attain with lithography, modern CMOS lithography, doing ordered, designing filters for phonons rather than taking what you get randomly with hot pressing and ball milling.
So you want to know about the controlled production versus the mass production.
Yeah, that's my hope. That's the next big increase.
Well, okay, so this is the answer that I've gotten so far from the industrial folks, and you may get different version. What you're talking about is costly, and in thermoelectrics, cost is a very, very large factor, because energy production, which fuel you use and which process you use, is largely governed by cost rather than efficiency. Although efficiency is related to cost, because you have very efficient process, then you get more bang for the buck, so to speak.
Thank you very much. Where is the